Okay, welcome back. This is class 3 of fluid mechanics, the University of Hartford ME340. This is class 3 video 1, and we're going to cover pressure and fluid statics. We're beginning chapter 3, and for this class we're going to do measurement of pressure, and we're going to include manometers as part of that. So first off, we have a couple of cartoons here, and what we're representing here is at least for static pressure, there's two kinds of pressure that we're concerned with. One is the pressure from all sides, that because of the surroundings, because we're constrained within something. And then the other pressure is because of you could think of it as the weight of the fluid above you, or you could think of it as the pressure because of the depth that you've attained, right? So there's those two kinds of pressure, and that's what these represent. Let's see, we have anything else? Oh yeah, and so for manometers, it can be a little bit confusing to try to gauge, or no pun intended, to be able to measure pressure with a manometer, especially when we have a more complicated situation. So we're going to use a method in which where we dive and we swim through virtually the manometer. And so as we swim down, it's positive. If we swim up, it's negative. And if we follow that procedure, we'll be able to sort out a more complicated manometer situation. So first off, we look at what pressure is. And just as you're familiar with, you could kind of think of it as, the same type of thing that we're going on with stress, right? We have force over area. And here pressure acts in all directions equally onto an object. With the slight caveat that the pressure increases as you go downwards. And we call that a pressure gradient, that change in pressure as we move downwards. And in this first video, you could probably skip to the second video, I think. Yeah, we probably will. And I will skip through some of this during class because it's kind of a longer derivation. But if you stick around here, you'll see, you'll get something out of this. What we're going to do is we're going to do a little derivation on like a little wedge of fluid. We're going to put pressure on all sides of it, and we're going to demonstrate there is an equation that we could come up with for fluid statics, which will this will also help us when we start to get into fluids that are moving as well. This derivation, it's sort of a proof. It's kind of one of those answers to like, I'm going to tell you something, and then you're going to, well, I'm skeptical, prove it to me. So that's really what our goal is right here. So we're talking first at pressure at a point, and we're going to prove Pascal's law that the pressure is the same in all directions, with a slight little caveat that, if we look at it, if we take a little step back from that idea that pressure is the same at every point, and we look at a more global, we'll see that pressure does increase as we go in further in depth. All right, so let's go ahead and change over to the document camera. Here it goes for our notes. Okay, so pressure is the same in every direction. That's Pascal's law. That's if we're static, right? So static pressure at a point is independent of the direction. And as we said, there's two types of static pressure. There's the kind that's pressure due to being constrained or due to surroundings. And so we're like inside a pipe, right? So it's constrained inside a pipe, and therefore we can have pressure coming in. And then we also have pressure due to depth. And we can think of this as the weight of the fluid that's above us. But something interesting, it doesn't necessarily have to be directly above us. So we can kind of show instances where we might have some type of weird looking vase or something like that. It just matters the depth to the top surface compared to us. And it doesn't have to be so the weight doesn't have to be directly below us, but we have a pressure gradient that increases as it goes down. So we have this little wedge, this little arbitrary piece right here, and we blow it up. And we first assume that maybe as part of this, we have a pressure on the left, maybe. Well, I think I started in the X direction. So we're going to go in this direction first, in the X direction. And take a look at a pressure that's acting. Yes, let me first look on here. Just I want to get this the right way for the direction that the thing is moving. This is the X direction. So what we're going to face on one side, let's call it a in the positive direction. That's going to be PX is going to be acting on that, right? So the force that we would balance onto this thing is going to be PX times, we'll call it, of course, it's across this area, which is going to be a triangle because it's a wedge, right? And so this is going to be 1/2. We'll call it just the length of each side right there. And so that's going to be del d. Let's go del dy as the base and del z right there, right? So this is the pressure on the x side times the area of that triangle. The same thing can be said on this side over here, but let's go ahead and assume in the beginning here that okay, so that's just going to cancel each other out, right? So we're going to actually see, we're trying to prove that they're the same on all sides, right? That in all directions, all the pressure is going to be the same. So here, in the sum of the forces in the x direction on this wedge, we're going to take px, right? And that's a lowercase p, and go, I forgot my 1/2 because it's a triangle, p y, I decided dy and dz. We're really messing this up, right? So that's going to be in the positive direction, the positive x direction, but we're also going to have in the negative x direction. So minus, and we have px in the x direction, and we have 1/2 del y del z, right, is equal to 0, and therefore we have the same pressure in both directions, and we can say, duh, no kidding. So here's where we might take a look at something that is actually part of the proof, right? So we're looking at a PS, right? That's going to be the pressure on this surface right here. And we're going to see, does it equal the pressure in the y direction, right? So the y direction is right here, and the angle of this wedge is a theta right here. So coming back up into here, let's see, I can zoom out a little bit so we can get both of those things in here. So we're going to say on the y surface, which is over here, right? That's the y direction. We're going to have, we'll call that the positive direction, py, and that is just a square, right? The other one was a triangle on the side. So we have del, let's call it x. That's this dimension right here. So we're dealing with that area right up in here. Times del z, right? So that's a force in the x direction, or excuse me, in the y direction. And now let's take a look at the component of this in the y direction. All right, so that's going to be negative because it's going to go that way, the component that we're looking at for this one. Zoom, come on, zoom a little bit. Focus a little bit better, right, please? Yeah, thank you. And so we have PS. And the area of this, well, okay, so first off, we had the width of that area is going to be del x. But now the height, I should say, yeah, so we're going to take a del s right here, which is going to be this length right in here, but it's only going to be the one that's in the vertical position right there. So that's the sine of theta right here, which we happen to know is also the same thing, should be equal to del z right there, is going to be equal to 0, right? So taking a look at those two things, because we know this length is the same as there, we can now say that py is equal to ps, right? So we know that they're in the same direction. Finally, with the z direction, now that's going to, the z is the vertical direction right there. See the vertical, they decided to go z this time. We'll take it from the bottom, pz, and that's just a del x, and del y is that area that thing is acting on, right, in that plane. And in the negative direction, we have ps, and it's areas we have the same width right there, right? We're looking at that area right there, and we'll have del x. And now for, once again, the surface right here, we have del s times the cosine of theta right there, which we happen to recognize is the same thing as del y, right? Right, so del y is this length right here, so we have the cosine of that. So, and then, but we also have, by the way, in the z direction, we also have the weight, and that's going to be minus del 1/2 del x, del y, and del z, right? This is the volume right here, and gamma is the specific weight. So this is the volume of the wedge. And so what we conclude from this right here is that we're going to have, you would see that we have some things cancel out right here, right? So we have del x and del y, they're going to cancel out. And this is del x and del y, so they can cancel out. And there's del x and del y. So what you could say is that pz minus ps minus gamma, and we should say 1/2 del z is equal to 0. All right. So, but for very, very small del z, right? So if this is very, very small, that del z, we say that p z is equal to ps, right? And therefore, they must be pz must be equal to py, right? And we could do the same thing in any direction. So we could just sort of prove that the pressure is going to be the same in every direction, as long as we're dealing with small values of incremental z. That doesn't mean the z itself is, I mean, we could be very deep in the depth, but if you're just looking between different increments of depth, it'll be very small. I'm going to keep on going with this video because I don't expect people to watch it in great detail here, but the next part of it is sort of a similar type of setup, right? To look at a larger cube. Let's see. So I'm not sure if I want to include this during our class. All right, so here's more of a, I'm going to say grad school, but on our way to grad school type of treatment of this is something we want to talk about the word gradient right here. And what is a gradient? Maybe you're familiar with the GRAD or this function right here, right? It's an upside down delta right there. By definition, it's the partial derivative of each of the terms of whatever parameter might be inside here. So we're going to look at the pressure gradient, which looks like this right here. And pressure is a scalar. It doesn't have direction, but we take a gradient of that pressure and it becomes a vector, right? We could have, because we have an I, J, and K component. So we're really looking at how does the pressure vary with each dimension and in which each direction. And so to pull it apart, we take a cube this time instead of the wedge that we did before. And what we want to try to do is prove this equation right here. And this is the beginning of the vector treatment that we want to have and we want to take a look at within fluids, right? So it has a purpose to cover it. So just keep that in mind. So once again, we do the FBD and IBD of a cube, right? So I didn't draw the IBD, but we could, right? So we have then this is kind of three-dimensional there, where we have the FBD, and it's going to be equal to the inertial body diagram, right? So it's because it is dynamic, and I didn't draw them equivalent here. Let me fix that up there. I don't know what's going on with my drawing skills have fallen away. Okay, so I drew basically a square and then extended it to a cube right there. So here's the FBD and here's the IBD, and we're looking at all these forces that are being placed on this. and on all sides, and they're all going to be pressures acting on areas, but then we're also going to have the weight as well, right? So we'll have another force placed in there, and I don't want to cram in all of our stuff. And then we might also see that we have like motion, and I will pull all the motions in the positive direction. And what we'll have mass times acceleration in the, let's see, I guess I decided that's the, in this case, this is the Y direction, X direction, and Z direction based on this figure right here. And what we'll notice right here is that we have on each side, we have a pressure going in the positive direction, right? So in the positive direction, but in the other direction, we have the pressure and then any kind of change in pressure, right? So we're going to have like at the origin that we're looking at here on this surface, and then this bottom surface, acting on them is the pressure at a point. But this cube is big enough that like we'll have an incremental change in the size of this, and the pressure could be a different value on the other side of that cube, right? So that's the idea here. We'll only do it for the X direction, and in the Y direction, we'll see that it's just similar so that we can just accept it. So breaking this down in the X direction, we'll say that the pressure, because it's equal at every point, so right here is the point about which that we're kind of like analyzing. That pressure in the, I guess it's this one at this time because it's in the X direction, so it's on the back of it, times our dy dz, right there, minus the pressure, let's say I got to get a parentheses here, pressure plus a differential pressure. That's the pressure that's like, because we moved from this point, from this back face over to this front face, we have an additional assumed del x going on. But we also need to multiply that by dx right there, I believe. Yes, dx. Is that right? Yes. So I think actually these shouldn't be dels anymore. We're going to make them bigger, so they're d's, right? So they got just a little tiny bit bigger. And then, okay, so that's the pressure, but now we also going to have dy. Yeah, it's the dx, dy, we have dy and dz for the area that is working on. That's the front face right there, that pressure acting on that front face. And then we're going to assume that it's going to go times mass times acceleration in the x direction, right? So we take a look at this, and first we note that we're going to have this guy and the combination of those guys are going to cancel each other out, right? So what we're left with is negative del p del x, right, times all right, and we can also divide this. You'll notice that dx dy dz, right? So let's do it in steps. Dx dy dz right now, because this p got canceled out right here off of this, so all we're left with is that gradient. Oops, I should have moved that down. It's going to be equal to max, but we note that we could divide through by here because that's going to be the volume. So what we can say now is negative p dx is equal to density times acceleration, right there, right? And we could say similarly in the y direction, we would get negative p del z equal to density times the y direction of acceleration, right? Now the last one here, we have to do something different because in the z direction, which we consider the vertical direction, we have an additional term, right? So we have pressure times the area dx dy, right? That's in this case, this one is the bottom face because there's the pressure war going in the upwards direction, so that makes that positive right here. And then in the negative direction going downwards, that pressure times whoops, made a mistake. Got to go in parentheses, right? Because it's the pressure that's on the top, which could vary. It could have an increased amount. So we have plus del P del Z times dz, right? And this is going to be that. So this is the pressure on that top face, and we're going to have d x dz. And then we also going to have in a downward direction, we're going to have the gamma times the weight of this, and that's going to be dx dy dz, which is the volume, and that's going to be equal to the mass times the acceleration in the z direction. And we do the similar thing as we did before, right? This one's going to cancel out because of that times that right there, right? And then what we're going to be left with is del P del Z times del Z, del X, del Y. Sorry, I messed that up. And then minus this. So we're going to be able to bring out the volume of these and divide over to the other side. So what we're left with is del P del Z minus gamma is equal to rho AZ, right? So what this really says right here is when we combine these three together, we recognize this del P del X, and this is supposed to be a Y. Damn it. I'm not going to fix it, but we can assume that you saw me making that mistake as I'm stammering through this thing. That guy, he needs a del in him. This guy, and this guy is equivalent to this gradient, right? And this only happens in the z direction. And here's our density, right? So what we see right up here is we've proven this equation right here, where this right here forms a vector, even though even though pressure is a scalar, its gradient is a vector. It changes with position in each direction, but we're saying that we know that that's how it moves. So if there is a differential pressure, that's what we mean by it. And then minus the gamma times k, because that's only in the z direction here, is equal to the density times the acceleration, and that is a vector, right? It's bolded here, but we could put a hat on top of them to double it. And then lastly, and I know this went on longer than I like my videos to go, and now if we want to, instead of this equation, we'll note that when the acceleration is 0, so this is the static condition, right? So we had the dynamic position up above, which we will return to at a later date. We'll return to this. In the special condition when we're static, we can know that we'll put in as a negative del P minus gamma K is equal to 0, right? Well, we could obviously have made them both pluses right there. But we'll note that when we're only looking in the z direction, that we're going to have del P del Z is equal to negative gamma, right? So we could have just written this down and you could just accept it. But I think putting it into the context of how pressure varies, here's our static pressure gradient that we will be using in this class today, right? So for today's class. So the conclusion is the pressure gradient is only, with an L in it, only in z direction, or in the vertical direction, when the fluid is at rest. So that is our conclusion for today. So let's see if we have any other slides that are relevant left in here. No. Pressure at a point is the same in all directions. That's the important thing right there. And for whatever reason, I decided to put the compressible and incompressible of it. We're mostly concerned when it comes to this with incompressible fluid, well, obviously liquids. You have that pressure gradient. The pressure gradient for a gas is really, really small, right? Just like, air gets thinner as you go up in altitude. So that's the equivalent there, but the change isn't nearly as dramatic because it's not as dense. So the end.